Have you ever wondered how a computer, a machine that really only thinks in black and white, in simple ones and zeros, can possibly understand the infinitely complex, colorful world all around us? Well, today we're going to pull back the curtain on exactly that, how industrial computers, or PLCs, translate what's happening in the real world into a language they can actually use. Okay, so let's jump right in. We're dealing with two totally different worlds here. Over on the left, you've got analog. See how it's smooth, it's continuous? Think about dimming a light switch or the temperature slowly rising. Now look at the right. That's digital. It is anything but smooth. It's just a series of clean, sharp steps. It's either on or off, a 1 or 0. There is absolutely no in-between. And that's the big question here, isn't it? How does a digital brain, like a PLC, that only gets those on or off steps, make any sense of our smooth, continuous analog reality? How do we possibly bridge that gap? All right, let's kick things off with our first section, the analog signals journey. We're going to follow a signal right from the source, a sensor out in the real world, and track it all the way to the brain of the machine. You know, it all starts with this, an analog signal. So imagine a temperature sensor inside some giant industrial oven. As that oven gets hotter, the sensor doesn't just send a message saying, hey, it's hot. No way. It sends out a voltage that is perfectly proportional to the heat. So maybe 10 degrees is 1 volt, 20 degrees is 2 volts, and on and on. That smoothly rising and falling voltage, that's our analog signal. Okay, so now for the really cool part. The digital translator. This is all about converting the physical world into the language of computers. Because that smooth, beautiful voltage signal, it's complete gibberish to a PLC in its raw form. It desperately needs a translator. And that translator, it has a name, the analog to digital converter, or ADC for short. It's tucked away inside the PLC's input module, and it has one single, incredibly important job. Take that analog voltage coming in and turn it into a digital number that the PLC's brain can finally understand. Now, to get what it's translating to, we have to understand the alphabet, and it all starts with a bit. A bit is the absolute smallest piece of computer information there is. It can only be one of two things, a 1, which means on, or a 0, which means off. That's it. So you might be thinking, how in the world can you represent a whole range of temperatures with just ones and zeros? Well, it's actually pretty clever. You just string them together. Just like letters form words, bits form binary numbers. You can see here, by combining just 4 little bits, we can represent all the numbers from 0 all the way up to 15. This right here, this is the language of binary. All right, next up, we have to ask, how good is this translation really? This is all about understanding resolution and range, because a good translation isn't just about getting the words right. It's about understanding what they actually mean. It needs precision, and it needs context. Let's talk about resolution first. I want you to think of it like steps on a staircase. If you have a really long staircase but only a few steps, each step has to be huge, right? It's clumsy. But if you have lots and lots of tiny little steps, you can move up and down much more precisely. For an ADC, the number of bits it has determines the number of steps. So, more bits, that means more steps and a much, much more precise measurement. And you can really see the difference here. An 8-bit converter, which uses 8 ones and zeros, gives us 256 distinct levels, or steps. But check this out. A 12-bit converter gives us over 4,000 steps. That is a huge leap. It means the 12-bit converter can spot tiny, tiny changes in that original analog signal, giving the PLC an incredibly accurate picture of what's happening in the real world. But, and this is a big but, here's the catch. A 12-bit converter spits out a super precise number, which is awesome. But what does that number actually mean? On its own? Absolutely nothing. It's completely meaningless. We've got the precision down, but we are totally missing the context. Okay, so take a look at this 8-bit binary number, 1000000. If you do the math in decimal, that's the number 128. It's exactly halfway to the biggest possible 8-bit value, which is 255. So, what does 128 mean? Does it mean the oven is at 128 degrees? Is the tank 128% full? Is the pressure high? Is it low? Without a scale to measure it against, a range, it's just a number floating out in space. It has no connection to the physical world. And this is where the signal range becomes absolutely critical. We have to tell the PLC's input module what kind of signal to expect. Are we sending it a voltage from 0 up to 10 volts? Or maybe it's a current signal from 4 to 20 milliamps. Now look at the table. Our number, 100,000,000, which is exactly halfway, suddenly has a specific meaning. If we've set the range to 0 to 10 volts, it means 5 volts. But if we're using that 4 to 20 milliamp range, it represents 12 milliamps. The range is what provides the context that turns a raw number into useful information. And that brings us to our final section, the payoff. It's time to put that digital value to work. We've taken a physical property, turned it into electricity, translated into a precise number, and given that number context. So now what? So let's just do a super quick recap of the ADC's job. First, it samples the analog signal. It takes a little snapshot of its value at one specific instant. Second, it quantizes that value. which means it finds the closest digital step on its staircase. And remember, its resolution determines how many steps it has. And finally, it encodes that steps value into a binary number and sends it off to the PLC's brain. And boom, that's it. The journey is complete. That smooth, wavy, and once completely unintelligible analog signal is now a clean, precise digital number that the PLC can read, understand, and, most importantly, use in its program. And that right there, that is why this all matters. Because now, the PLC can run simple but incredibly powerful logic. The program can just say, if the digital value from that temperature sensor, which we now know represents actual degrees, is greater than 100, then turn on the cooling fan. This is so critical, not just for ovens, but in industries like pharmaceutical manufacturing, where a temperature being off by just half a degree could ruin an entire expensive batch of medicine. From a physical feeling, to a digital value, to a real-world critical action. That is the power of this translation. So it kind of leaves you with this one final thought, right? We've gotten really good at turning things like temperature and pressure into data, but as our ADCs get faster and our resolutions get impossibly finer, our machines are getting incredibly better at sensing the world around them. It really makes you wonder, what's the next human sense they're going to master? Smell? Taste? Maybe even touch? The possibilities are pretty fascinating to think about.